back to my channel. So as we have agreed that we will use a real, let's see, project, or let's see, industrial project in our ML ops. So what we already agreed that we can use anomaly detection. So today we are diving into PaDiM, which is it's a batch distribution modeling for anomaly detection. So imagine you have a system that can spot the tiny, let's see, defects and faster than a human inspector. And that's exactly what PaDiM delivers. So PaDiM, it's, as I said, stands for batch distribution modeling, and it's not, let's see, uh, another AI buzzword. It's just a game changer for framework that combine the power of deep learning with practical industrial needs. And I think most of the companies are using this algorithm. And whether you are in a manufacture, quality control, or surveillance, this presentation will show you how the PaDiM is setting new standards in anomaly detection. Let's explore. Let's see how it's working. So let's start with the basic stuff. What exactly is anomaly detection and why should we care about this? And as you can see in the anomaly, you are running, let's just as example, you are running a factory producing thousands of components every day. So among of these thousands, maybe just one to have defects. And how to find these defects? Finding these defects, maybe anomaly could work, right? But finding this anomaly manually, it's a time consuming, expensive, and also it's prone to human error. Why? So sometimes when you have, this is my experience, when I have a defect, I'm just seeing a defect, right? But also my colleagues have see it's not a defect, and he has some, let's say some argues, and they have some argues, and when you see, it's hard for a human even to recognize the defects because it's working with so PaDiM is working with pixels, and it's really impressive, and I recommend you to indeed to use it. So anomaly detection is this, I would say, it's a superhero solution for such problem, and it's a process automatically to identify patterns that that didn't let's say doesn't belong to a good behavior. So as you can see here, so for instance, you have this behavior here, and here suddenly you have this behavior in this point here, and so you see, I mean, just you can recognize that, yeah, it's here something it's not normal. Maybe something is happening here. So regarding the images, we have to detect, let's see, the pixels. If the pixels have, let's see, a different behavior from what we already, let's see, trained. So in the industrial setting, the technology is absolutely, let's see, crucial. It means the difference between two images, let's see, or two products is really making a difference. Imagine you have a building, I don't know, maybe a medicine, or maybe this pills of medicines, and you have to have to make sure that everything is covered correctly, and no defects in this, no scratches, and sometimes in industrial, let's see, an automotive, for instance, BMW, they need to make sure that the car's pens has no defects, and everything is consistently and without any defects, let's see. And there are, let's say, some key challenges here. Why? See, some guys will say, I can detect anomaly with supervised learning, but supervised learning, here we have one problem here: rare anomalies. So you don't have two classes. Of course, you have two classes, but the anomaly images, you will not have it as the normal images. So the normal images, you will have 10,000s of images, but the anomalies will be 10 or 20, which is imbalancing, which doesn't make any sense to use uh, uh, supervised. And the second one is here unexpected patterns. Sometimes you have a defect here, sometimes you have a defect in this point, sometimes you have a defect in this point, and it's unexpected patterns, and it's not, let's see, easy to see. Here I have a defect. This one is the defect. So it's not easy for even for a human, and it's also one class learning. So you have only one class learning and also real-time processing. You need something really fast. And I will show you. I have optimized algorithm to run in a 5 milliseconds on a GPU and maybe 50 millisecond in a CPU. I will show you all this and also show you optimization. And let's see here, there are some limitation of the existing methods. Somehow there are several methods that try to detect the defects or let's say the anomaly. And for instance, this autoencoder and gangs, it was working. I have tried also this one, but what is the problem with autoencoder? You have to, if you have many images, if you have new images, you have to retrain the network of the autoencoder, which this somehow takes, sometimes it takes a days to just to get the model. And then the second problem that I have seen, I have, let's see, faced, it was the generalized. So sometimes it's even the error, the defected images. When you try to reconstruct the defected images, it will try to see, this is fine. It's so that's why it's autoencoder is generalized method, and the embedding similarity with KNN and SPIDA. So this is also one of the anomaly detection algorithm. And the problem here is that if you have a big data set, and let's say, for instance, if you use KNN, and you have one image, and you have 10,000 images, just for sake of simplicity. And to calculate the KNN, you have to calculate the distance between this image against the 10,000 images, which is time complexity. And it's really, I mean, it's not needed indeed, and this is somehow the limitation of the existing algorithms. And let's see here, we need somehow a good solution, which is the PaDiM. And the PaDiM, it's let's see, use the pre-trained CNN, extract the features from the from the images from the several layers. I will show you in a moment, and use these features to uh, calculate the Gaussian distribution for each pattern, for each position, and then in the inference we will calculate the distance from the model itself, from the Gaussian distribution against the image features, not as a KNN. And here we can see we have calculate, if we have a pre-trained CNN image, CNN, let's see ResNet. And for the ResNet, we have, let's see, 3 or 4 layers. And we can extract these layers, and here we can see, we can, let's see, guarantee that there's a semantic correlation between these features, and which should be a good for the localization. And as you can see here, it's, let's see, oh, so here, for instance, let me just when it's this one and one, we have the extracting these features from the trained model from different layers, and we have concatenated or embedding these vectors, and then added to the to the Gaussian distribution. And you can see here this is vector concatenation, and then embedding collection. Then the next step is to use the the building the Gaussian distribution. And for the Gaussian distribution, you will need to have the mean and covariance matrix. For example, in the training, it will be, let's see, it will take much time, but I have improved the time of the training and also for the testing, for the inference. And for the training, I have, let's see, 200 images, just as example, 200 images. It will take only less than 500 millisecond, or let's see 1 minute. Regarding related to the training, it's not that matter. So the most important one is the inference. But although it save your time if you have, let's say, some issues, or so that maybe you need to add some images. The training process will take, let's say, I will just say roughly 1 minute. And for the anomaly detection, we will calculate, we extract the same features from the test image, and calculate the distance with Mahalanobis distance. And this Mahalanobis distance, it's not like KNN. It's calculating the distance from this point to the distribute for the Gaussian distribution. And it's really fun. I also improved this much, and it was working perfectly fine. And what is the advantage of the PaDiM? Of course, there are several algorithms and also several improvements of this, of PaDiM. And why I like this PaDiM? Because I don't need the, let's say, the defected image during the training. So I need only one types of images, which is okay. And I don't need, let's say, thousands of images. If you have only 100 image, 100 to 300 images, this will be more than enough. And the time complexity is one. It depends indeed in the image size. And of course, I will show you now the data set. Before the data set, let's say we are using MVTech dataset, which has 15 class, and each class has 240. And imagine if you can build a model and real model for inspection with only 240 images. This will be a great, let's see, impact in your, let's say, industry. And you can see sometimes you will get for such a data set, you will have ARC, I mean AROC 99%. And one disadvantage of this, I will say, is that sometimes, let's say, you have new images. Let's say for the, I'm not quite sure. Maybe like just as example, transistors. But if we would like to use a ResNet, the ResNet itself hasn't seen any images like this. So maybe the features will be sensitive, or maybe not okay. But for such, I mean, tried different data set, but it was working. But in case in your data set it's not working, you have to, let's say, build a model or train a ResNet on your data set to build a model, and just try to collect any different from different data sets, and this should work. And now let me just show you the data set. So this is the data set, and you can see here, this is the 15, 1 2 3 4 5 6. Yeah. And you can see this is the objects, let's see, the inspection that it's used for this. And if you see now the PaDiM implementation, the original implementation, it was really slow. And I have also taken some codes from different repos, and have also worked on this and optimized it. And I will show you next time, because this is really important, at least for this project, because we will use MLOps and Kubernetes and everything. We will use this to train our model, our PaDiM, on the cloud as well, ML, and then we will try to making the inference and see the other pipelines. That's it for today, and thanks for watching. If you like this video, please subscribe into my channel, like the video, and also if you have any question, just drop the question in the comment below. Thanks for watching, and see you next time.